Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we'll discuss a new topic regarding specific speed of a centrifugal pump. In our previous lecture, already we have discussed regarding the working principle of centrifugal pump, and also we have discussed regarding the minimum speed required to start a centrifugal pump. But here, we'll discuss about the specific speed of a centrifugal pump. So to understand the specific speed of a centrifugal pump, first of all, we need to remember or we need to know how the centrifugal pump is working. If you have seen previous videos, then obviously you understood or you will remember. So let me just give a brief idea about how the centrifugal pump is working. So we have a impeller part is there, which is mounted on the shaft. Okay, and this impeller, like it is connected to the suction pipe, and the suction pipe is connected to the reservoir, and the reservoir is nothing but the sump level where the storage of water or reservoir of water is there. So that is called sump, and with the help of this suction pipe, we used to lift the water from the sump level, and after the water came from here, and it is going to strike to this impeller, and in the impeller we have the number of vanes, that is okay. So these are the vanes are there, and after striking this one, it will go out, and that is called our delivery pipe. So from with the help of this delivery pipe, the water is supposed to be delivered to the estimated positions, you can say. So the distance you can see from this sump level or from this water surface to the place where the water is supposed to be delivered, this distance, this total distance actually is to call the head. It's called the head, total head, or is to call it as also, it is to call it the manometric head also, we used to call this. So this one actually we used to indicate by HM. But here the specific speed actually it describes or defines the speed of a the speed of a geometrically similar pump. If I consider similar kind of pump, a geometrically similar kind of pump which will deliver 1 cubic meter of liquid, 1 cubic meter of liquid per second, okay, against a 1 meter of head, against a 1 meter of head. The same thing what I told you, okay, similar things is there. That means this is the work of a pump. If I consider a geometrically similar pump, another one, okay, and when I can say it is a specific speed, when the specific speed will be considered when like 1 meter cube of water, that means the discharge, this is our discharge and this is our head. So when this much discharge will delivered with 1 meter of head, and then we can say the speed is converted to, like, speed can be specified as the specific speed. So I hope you understand. So here also, like, you can say if a normal pump is there, without thinking any second thought, let's see, this is the pump is there. So here we may have like discharge of water maybe like q equal to 50 meter cube per second, suppose, and here it's a total height or total head of this maybe like 500 meter will be something will be there. Okay, in this case that is the working of a pump, we can say. But when we can say the specific speed of a centrifugal pump, that means we need to consider the speed of a geometrically similar pump which will deliver 1 cubic meter of water per second, or we can say 1000 liter per second, okay, against a head of 1 meter, okay, then it is called specific speed. So the specific speed is denoted by ns, okay, and we need to find out here the expression for the ns. So to derive this equation for the ns, we need to go through some steps before going to derive this equation. Let me tell you some basic applications, or why it is required, or why the specific speed is required to learn or to study. So let me tell you. So this specific speed will help us to identify which impeller design is suitable, which kind of impeller design. So it is required for the impeller design. Which kind of impeller design is suitable, that will be identified. So in the specific speed also we have like low specific speed, one is there, another one is there medium specific speed, another one is high specific speed. So different kind of specific speeds are there. So in that low, medium and high specific speed also we have different applications are there. So the low specific speed, it will be used for radial flow pump. It will be for radial flow pump, and this will be used for the high head. This will be used for the high head and low discharge. This will be used for the high head and low discharge, and this is required, for mixed kind of flow. So mixed flow pump, it will be used, and this also I can say that will be moderate kind of moderate kind of head as well as moderate discharge will be. For this kind of things we will require medium specific speed. For the high specific speed, and this will be used for like axial flow pump. You can use this for this, or you can high specific speed will be used for this one, axial flow pumps. And this also will be give you like low head, okay, low head and high discharge reverse, okay, because it is a high specific speed, so high discharge, low specific speed, low discharge. Now these are the requirements, or you can say indication of specific speed, or the specific speed will be used to identify which kind of impeller design is required or suitable, that will define. Now we'll derive the expression for the specific speed. So to derive this expression, first of all we need to write the discharge formula. So discharge of a centrifugal pump Q, we know that area into velocity. So area into velocity, area equal to, we know that the area formula we can write pi into d into v, and the velocity we can write this is vf. So here if you see, the Q is directly proportional to d into b into vf, is directly proportional to this one, and this one I will give the equation number 1. So if you see the diameter and this width, this is be the width and this is the velocity of flow. So we know that the diameter of a pump or diameter of the impeller is directly proportional to the width of the impeller, the outlet condition. Okay, so these two things, like we can write directly proportional. Now if both are directly proportional, we can write this value of b in terms of d. So I can write Q is directly proportional to d square into vf. Just I'll put the value of d like value of b here. So d into d, that is d square. So this one we can write, this is equation number 2. Now this is about Q. Actually I need to find out the value of ns, specific speed, and the specific speed will be identified, like it need to be derived in terms of Q and HM, because at a unit speed, like unit discharge and unit head as I consider. Now for this again I need to consider, we know that the tangential velocity u equal to pi dn by 60. This is the formula we know. Now if you see this value, like the formula here, this is constant, this is constant, so u is directly proportional to d into n. Okay, u is directly proportional to d into n. This one I can write here. Now again I'll try to convert this value of d in terms of either q or n. Okay, so for that what I'll take, now we know the value of h or hm, we can say, is directly proportional to u square by 2g, u square by 2g or u square by g, I can say. So here if you see the hm, I can say is directly proportional to u square, or only head if I write also, I can write u square by g. So there also one more equation we have seen, u square by 2g minus u1 square by 2g equal to h. There also we have seen previously. Okay, that is the total head, the difference of this kinetic head, I can say kinetic head equal to the total head here. Anyway, hm you can write in terms of u square, and here I can say that u is directly proportional to root over of hm. And apart from that also we know that the tangential velocity u is directly proportional to the VFM or VF. Okay, the VF is what? VF is nothing but our velocity of flow. So if by this concept of these two equation, we can conclude this like U is directly proportional to VF and directly proportional to root over of HM. Okay, this one, let me give equation number 4. Now, if I put this value of here in the previous equation in number 3, or else if I consider the value of these and these, then what I can write here, like root over of HM is directly proportional to D into N. And here I can write like D is directly proportional to root over of HM by N. Okay, this one I can write. Now we got the value of D. Let's put the value of D in the equation of second, like 2. So by putting the value of D in the equation 2, we can write Q here directly proportional. Here we'll get now here D square is there, so we can write this D square is nothing but root over of HM will be HM only, and here it is N square and into VF. So again, if you see this equation number 4, VF also directly proportional to root over of HM. So I'll put the value of VF in terms of HM. Then I can write Q is directly proportional to HM by N square into root over of, this is HM is there. Now this one, if you see HM and the root over of HM is nothing but 1 by 2. If I'll just solve it, then I can write Q is directly proportional to HM to the power 3 by 2. And this is N square. Now this one we can write Q equal to K into, I can write put a value of constant of proportionality, that is K. So K HM 3 by to the power 3 by 2 divided by N square. Now here K is the constant of proportionality. Here you can write K is the constant of proportionality. Okay. Now what is our intention? Proportionality. We need to find out the value of Ns. Now when you can find out the value of Ns? Now when the value of Q is 1 meter cube per second, and there we need to consider the value of HM is 1 meter. Then we can find out and here we need to consider the value of N equal to Ns. Now just put all this value in this equation, we'll find out the value of K. So Q equal to 1 and K HM to the HM value we can put 1 to the power 3 by 2 and divided by here Ns square. Now if you solve this one, we can get the value of Ns square equal to K. Now so all this value we got here. Now we'll just put this value in the equation of here. If you see this equation, this one, like equation number 5 I have not given. Let's put the value of K in this equation. So we can write Q equal to, here how much is there? K value is now Ns square. So Ns square HM to the power 3 by 2 and this is N square. Now as I told you that we need to find out the value of Ns square. So Ns square like Ns we can write this is Q into N square, Q into N square divided by HM to the power 3 by 2. Now this square I'll take it to this side. So we can write finally Ns equal to, this is root over of now N square will be N and Q will be root over of Q, and this is HM to the power 3 by 2 is there. Now this square came, so we can write this is 3 by 4. Okay, so this is our final requirement or the final answer for the specific speed of a pump. So I hope you understand this derivation, though a slight complication, like we need to assume some assumption something is there. We'll need to start from the Q here. Okay, this continuity equation we need to start, and after that we need to consider this value tangential velocity. Then from that we need to go for these values like HM is directly proportional to U square by 2g or U square by g. Also we can write there, this is the constant value. We can write HM is directly proportional to S square. Okay, and then from that we can derive this equation. So I hope you understand this derivation. If you are having any doubt regarding this, you can give a comment on the comment box. Thank you all.